Hey everyone, it's Suraj. We're going to be walking through the homework 1 from the spring 2019 iteration of this course. I can't guarantee that I'll be able to do this for every homework that we'll have this semester, just because it's very time consuming. But I think for homework 1, since we introduce a lot of the notation that we'll rely on throughout the semester, I think it's important that everyone sort of understands how to attempt each of these problems. So let's get into it. So question 1 is just a student information form, so we really want to look at number 2, where we're told that A1 through AN are all subsets of our set A that are all disjoint, meaning that, for example, A2 and A3 share nothing in common, A2 and A4 share nothing in common, and really no two subsets share anything in common, right? But the union of all of these subsets is A itself. So all of these subsets are disjoint, but their union makes up the set A. So let's draw a picture. Okay, and let's just say this entire box represents our set A, and let's divide this up into non-overlapping regions. We can say this is A1, this is A2, this is A3, A4, and A5. Notice they don't overlap, but their union is all of A. And now we're asked to consider some other set B, which I'll just draw arbitrarily. That's also a subset of A. And what we want to show is that the cardinality of B is equal to the sum of the cardinalities of the intersections of B with each of these subsets. Okay, so how we can do that is by counting 5 separate pieces of the set B, right? So B is enclosed in the circle. So what we can do is start by counting first the overlapping portion between B and A1, which is precisely cardinality of B intersect A1. Okay, plus now this region where B overlaps with A2. So we'll say plus B intersect A2. Then the region where B overlaps with A3. So plus B intersect A3. Plus this region here. Plus B intersect A4. And lastly, this region here, B intersect A5. Okay, so in this question, the goal is just to get you to draw a picture and understand visually why this is true. Okay, and this is all we really had to do. So all we're saying is that the cardinality of B, when B is some subset of A, is the sum of these little pieces, the intersection of B with A1, B with A2, so on and so forth. Okay, this is not a rigorous proof by any means because we just picked one example in the case when n was 5. So this is not like a formal proof for any case, but you sort of get the gist of why this happens to hold true. Okay, and in future courses, when you learn about things like the total probability rule, you will rely on this sort of principle. Okay, now let's look at number 3. Here, we're studying what's known as the principle of inclusion and exclusion, which, given two sets A and B, it's the problem of determining what the cardinality of their union is. And I know we also covered this in lecture, but it's so important that we'll go over it again now. Okay, so what we want to do is count every element in the the union of A and B exactly once. Okay, so a good way to start would be to count every single element that's in A. So we'll shade in this entire circle. Let's call that cardinality of A. Plus, we probably want to count everything in B as well, so I can shade in this region. Cool, but now what do I notice? The region that's shared between A and B, namely the, that's not what I meant to do, this region right here, the highlighted region, A intersect B, has been counted twice, right? I counted it once when I counted the cardinality of A, and then another time when I counted the cardinality of B. So I'm double counting this intersection, so I need to subtract the cardinality of this region exactly once so that every piece of the circle is counted just one time. Okay, so the final results that the cardinality of the union is the sum of the cardinality of A and cardinality of B minus the cardinality of the intersection. And this counts every single piece of this Venn diagram exactly once. Okay, now let's look at the case when we have 3 sets, A, B, and C, And we have the same problem, right? We want to count the cardinality of A's union with B and C. Okay, so one way we could start is by adding the cardinality of A, B, and C. Okay, so the cardinality of A consists of this region, along with this region, and this region. Okay, notice I've colored them disjointly so that I can erase as we go along to ensure that each region of the Venn diagram has just one color in it. Okay, is only colored once. Okay, so we have the cardinality of A. Then I'll probably go and add the cardinality of B. So I'll have this region, this region, this region, and this region. It's cardinality of B. And then why don't we make C green? So I count the cardinality of C, then all of these regions will get some green in them. And what do we notice? Are we done? No, because all of the regions with overlaps have been at least double counted, right? So the region that's overlapped just by A and C is counted twice, just by A and B is counted twice, and just by B and C is counted twice. And the triple overlap region in the middle is counted 3 times. Once for cardinality of A, once for cardinality of B, and once for cardinality of C. So we need to adjust for that because we want each region in our Venn diagram to be counted exactly once. So one thing we can do is start by subtracting all of the pairwise intersections. So the pairwise are, intersection of A and B, intersection of A and C, and intersection of B and C. Okay, so why don't we try that? So let's subtract the intersection of A and B, and to do that visually, every time that there's some shared region between A and B, I need to remove one of the colorings, okay? So A and B, I can remove those two, okay? Now I need to subtract A and C, which means I remove this and this, and then also subtract B and C, which means I subtract the middle and this region, okay? Now, every piece of my picture has been counted exactly once, except this middle region, which hasn't been counted at all now. It was originally triple counted, right? We counted it once for card A, once for cardinality of B, and once for cardinality of C, but I subtracted it 3 times, so now it's counted 0 times. I want it counted exactly once, so I add it back. Okay, now every region in my Venn diagram was counted exactly once, and so this is how you derive the principle of inclusion and exclusion for 3 sets. Okay, we won't really look at part C right now, but it's really just an extension of this principle. What you'll see is the result is for any number of sets, you'll add the individual cardinalities, okay? Subtract the pairwise intersections, right? So if you have n sets, you subtract the intersection of A1 and A2, A1 and A3, so on and so forth, all the way until the intersection of AN-1 and AN. Then add the triple intersections and subtract the 4-way intersections and add back the 5-way intersections and so on and so forth. But we don't have to worry too much about that right now. That's just to get you thinking about it. Okay, so number 4 is actually an extension of this problem. And it says let A and B be sets, determine the cardinality of the difference of A and B plus the cardinality of the difference of B and A. Okay, so let's take a look at this picture. What exactly does this want us to count? Okay, so what we'll do is first label what the difference between A and B is. And recall, A and B is the set of everything that's in A and not in B. Okay, so what's the region that's in A and not in B? Well, it's just this, okay? And similarly, what's B minus A? It's the set of everything that's in B and not in A. Okay, so that's this region over here. Well, this looks very similar to the union of A and B, just without the intersection, right? So what we see is that the cardinality of A minus B plus the cardinality of B minus A is just the cardinality of the union of A and B minus the cardinality of the intersection, right? It's the elements that are only in A and the elements that are only in B. We got rid of the intersection. So this is just the number of elements that are in the union minus this intersection, which is A intersect B. And conveniently in question 3, we were given what the cardinality of the union of A and B is. Well, that's just cardinality A plus cardinality of B minus the cardinality of the intersection, but we're subtracting the intersection again now because we want it counted 0 times, and it was originally counted once. So our result is cardinality of A plus cardinality of B minus 2 times the cardinality of the intersection. Okay, and so that's how you count the number of elements that are only in A plus the number of elements that are only in B in terms of the cardinality of A, cardinality of B, and the intersection. Okay, now let's take a look at question 5. So we're reminded of the definitions of the natural numbers, the whole numbers, and the non-negative real numbers, not the definitions, but the notation for them. And we're also given these definitions of these sets A, B, and C. And we want to determine the results after these set operations. So I think the best first step is to identify concretely what A, B, and C are. Okay, so first let's look at what A is. Well, it's the set of all prime numbers that are less than or equal to 25 that are in the set of whole numbers. See, we're told that our universe is the set of all whole numbers less than or equal to 25. So that means A will look something like 2, 3, 5, 7, 11, 13, 17, 19, 23, and yeah, that's it. Looks okay. B is the set of all numbers that look of the form 2k, where k is a natural number less than or equal to 12. Well, so all the natural numbers less than or equal to 12 are 0, 1, 2, 3, 4, all the way until 12, and we're doubling that because we have 2k, so our list looks like 4, 6, 8, all the way until 24. And C is saying, give me all the numbers that look like t squared, where t is a natural number less than or equal to 5. Okay, so the natural numbers less than or equal to 5 are 0, 1, 2, 3, 4, 5. And we're squaring them. So again, we have 0, 1, 4, 9, 16, and 25. Great. Okay, so let's take a look. First, we want the intersection of A and B. Well, here it probably helps to just look at the set builder notation definitions of these sets that were given in the question. We're told that A is the set of all primes, and B is the set of even numbers. Well, the intersection is the set of all numbers that are prime and even, but we know there's only one even prime, right? And it happens to be less than or equal to 25. It's the number 2. Okay, so that's the only element in the intersection of A and B. Now in part B, we're asked for the union of A's complement and B's complement. And remember, the complement of A is the set of everything that's in the universe that's not in A. Okay, so what we could do is go determine A's complement, which is the set of all composite numbers, or well, 1 in the composite numbers, and B would be the set of all odd numbers. And we can go through and find the union, but there's an easier way, and the hint sort of tells us this. We were told in lecture that De Morgan's laws states the following. Okay, it tells us that the complement of an intersection can be written as the union of two complements, and the complement of a union can be written as the intersection of two complements. Okay, so in this question, the first one actually applies because we already determined what the result of A intersect B was, right? A intersect B was just the set of the number 2. So its complement is the set of all the naturals less than 20, so not all the naturals, all the whole numbers less than 25 that are not equal to 2. Okay, because this is exactly what we're being asked for. Okay, so really this is just the set of numbers 0, 1, and 3, 4, 5, 6, all the way until 23, 24, 25. If we wanted to put this in set builder notation, we could say, give me all numbers that look like x, such that x is in the set of whole numbers, x is less than or equal to 25, and x is not equal to 2. That's the set B. And I realized earlier in this video I might have referred to our universe, this as being the naturals. That's the whole numbers. Okay, naturals do not include 0 for our purposes. It's the naturals. It's the whole numbers. And in this case, the condition you were looking at involved the whole numbers, not the natural numbers. Okay, so I apologize if I said anything that contradicts that a couple minutes ago. Okay, Now let's take a look at C. We want to find the union of A and B and intersect that with C. Okay, so first let's find the union of A and B. Well, that's going to be the set of all numbers that are prime or even, but we notice C is a much smaller set, right? Or list, set. It's just 0, 1, 4, 9, 16, and 25. So an easier way to reason about this is think about the elements in C that are either in A or in B. Okay? And all the numbers in C are squares, so none of them are prime, and so they're not going to end up in the list of B, right? They're not going to end up in the list A, because A is a set of all primes. And the set of numbers B are the even numbers, okay? So it turns out, when we take the union of A and B, and then take only the elements that are also in C, all those numbers are going to come from the set B, right? And the numbers specifically are 0, 4, and 16. Because if you want to translate what the query A union B intersect C is saying is, give me all numbers that are prime or even and a square. Okay? And this is sort of phrasing it as a propositional logic statement. No primes are also a square. Okay? So all of the numbers that are going to come from the first set are going to be the even numbers. And so a result just ends up being the set of even squares that are less than or equal to 25, which is just the set 0, 4, and 16. Cool. Okay, now let's take a look at part E. We want the difference between set A and the complement of set B. So what this is really asking for is, give me all elements that are in A and, give me all elements that are in A and get rid of all the elements that are not in B. Okay, so we want all the elements that are in A and get rid of everything that's not in B. Okay, and so the elements that are in B are the set of the even numbers. So the elements that are not in B are the odd numbers, right? And so since we know that 2 is the only even prime number, the numbers 3, 5, 7, 11, 13, 17, 19, and 23 are not in B. And since we want to get rid of the elements that are not in B, this result will just be the set of the number 2. We're just starting with the elements in A and removing everything that's not in B. And all of these odd primes are not in B. Okay, lastly, A's complement intersect B's complement intersect C's complement. What we're looking for here is a set of numbers that are not in A, not in B, and not in C. Okay, so for this, the easiest method might just be to visually look at all three sets and look at which elements are not contained in any of them. Okay, so let's see, 0's in at least one of them, 1's in at least one of them, 2 is, 3 is, 4 is, 5 is, 6 is, 7 is, 8 is, 9 is, 10 is in it, 11 is, 12 is, 13 is, 14 is because 14 is odd. And the first number we see that shouldn't be in any of these sets is 15, right? Because 15 is not prime, it's not even, and it's not a square. Okay, so 15 is the smallest number that's not in any of these three sets. Okay, 16 is a square, 17 is prime, 18 is even, 19 is prime, 20 is even, 21 is another number that's not in any of these sets. Okay, it's not prime, it's not even, and it's not a square. So you can add 21 to this list. 22 and 24 are even, 23 is prime, and 25 is a square. Okay, so it turns out the only numbers that are not in any of these lists are 15 and 21. Okay, another way we could have identified this is by taking the union of A, B, and C and finding the complement of that. And that's, again, an application of De Morgan's laws. Okay, I guess we didn't formally show that it holds for a collection of three sets, but this is something we'll look at more when we get to propositional logic. Okay, so the complement of A intersected with the complement of B intersected with the complement of C is essentially the set of numbers that are not in any of these sets. Okay, and it turns out that the only numbers that satisfy these conditions are 15 and 21. Okay, now we'll take a look at number 6, where we're asked to show that the composition of two surjective functions is also a surjection. Okay, and so let's assign G to be some surjection between sets A and B. So this is surjection, and let's say F is a surjection from B to C. Okay, and what we'll look at is the composition of F and G. So specifically, F, this circle G, really refers to the function f of g of x. Okay, and we want to show that it's a surjection. And to show that a function is a surjection, we need to say that for any element in its codomain, there's something that I can pass into it to get that specific element. So for example, if our codomain is a set of real numbers, I need to be able to say, I want my output to be 10 million. What's the number I can pass into it to get 10 million? Or do I know for sure that there exists some number that I can pass into the function to get the output of 10 million? Okay, and I need to be able to replace 10 million with any number in the codomain. Okay, so how we'll do this is in two steps. So the first is we'll use the fact that the function f going from b to c is surjective, and therefore this means that for all c in our codomain, right, and really this is the codomain both of our composition, but also just the function f, right, because these are the domains, and these are the codomains. For all c in our codomain, there exists some b in the domain of f such that f points b to c. So what we're saying is I want the output of f of g of x to be c. Okay? Well, if the output is c, what this is telling us is b is the number we can pass into f to get the output of c. And since f is a surjection, we don't need to prove that. We're sort of given that. We know that this b always exists. Since f is a surjection. Okay, we're already given that. So this means that we know that there's some number b that I can pass into f to get my output of c. So now, I'll sort of do this again. Since g going from a to b is surjective, I know for all b in the codomain now of g, notice that this was the domain of f, but this is the codomain of g, there exists some a in the domain of g such that g sends a to b. Okay? If we put these two statements together, what we're saying is, suppose I want my output of f of g of x to be c. What we get by combining the fact that f is a surjection and g is a surjection is that if I pass a into this function, i.e. if I evaluate g of a and then call f on that, I'll get my output of c for any c in the set big C, i.e. The codomain of f. For any c in the C, i.e. codomain of f. Okay, and since I made no assumptions of the c, all I said is that if f is a surjection, there always is something I can pass into f to get the output of c. And then since g is a surjection, there's always some element I can pass into g to get the output of b. But if I can get that output of b, since f is a surjection, I can also get the output of c. Okay, so what this is saying is there will always exist some element a that I can pass into the composition of f and g to get the output of c. Okay, so what this is telling me is for any element in the codomain of our composition, there's something I can pass into it to map to that element in our codomain. Okay, so this is a proof that the composition of these two functions is a surjection. Okay, I apologize if that wasn't clear, but please come to office hours if you have any questions with that. Okay, lastly, we want to determine whether each of the following functions is an injection, a surjection, a bijection, or none of these. Okay, and remember, for it to be an injection, what this tells us is if 2 points or 2 values in the domain map to the same output in the codomain, those 2 inputs had to be the same. And another way of looking at this is if 2 elements in the, I really should say for all x1 and x2 in the domain, if x1 and x2 are not equal, this means f of x1 and f of x2 are not equal. Okay, in a surjection, we sort of talked about it here. For every element in the codomain, there exists something in the domain that points to that element in the codomain. Okay, so let's look at A. And so our domain is the set 2, 3, 4, and our codomain is also the set 2, 3, 4. And the function is given by the set of ordered pairs 2, 2, 3, 2, and 4, 4. So this function is actually neither an injection nor a surjection. Okay, it's neither. And why is that? It's not an injection because f of 2 is equal to f of 3. Notice they both point to 2. But last time I checked, 2 and 3 are not the same number. It's also not a surjection because there's no, we can say this, there's no c such that f of c is equal to 3. Okay? Notice 3 is an element in the codomain, but it's not one of the outputs of the function. The only outputs of our function are 2 and 4. And for a function to be a surjection, that's just another way of saying the range and codomain are the same set. But there's nothing here that outputs the value 3, so this is not a surjection. Okay, so this value, or this function, is neither. Okay, B, the function that maps reals to reals given by x cubed, this is actually a bijection. Okay? And to show that it's a bijection, we need to show that it's both an injection and surjection. Well, to show that it's an injection, if we look at a cubed is equal to b cubed, we know that this implies that a is equal to b, assuming that we're only looking at real numbers. Okay? It's not like squaring, a squared is equal to b squared does not imply that a is equal to b because, one could be the negative of the other. But since our exponent is odd, we don't have that situation. We know that if two cubes are equal, then the roots of the cubes are also equal. Okay? And an easy way of looking at this is just by drawing the picture of x cubed. Looks something like this. And we see the function never outputs the same value more than once because it's strictly increasing. Okay, so this is certainly an injection. Is it a surjection? Yes, because given any real number that I want as my output, so suppose I want f of x to be equal to c, so i.e. x cubed is equal to c, the input I pass into the function is just c to the 1/3, right? Suppose I want my output to be 10 million, I just pass in the cube root of 10 million, and I'll get 10 million as the output. And that works for both positive and negative numbers. And you notice just by looking at the graph, our function extends infinitely, both in the positive and negative direction, so it'll eventually hit any real number value that I specify that I want as my output. Okay, so this is definitely a bijection. Okay, so now we need to look at C, which is given by f of x is equal to x cubed plus 3x squared minus 7x minus 2. So this one is a surjection, but not an injection. Okay, and if we're assuming that our domain and codomain are the reals, it's actually the case that every cubic polynomial, so polynomials of the form something x cubed plus blah blah blah, is a surjection. And the reason for that is because cubic polynomials will always extend infinitely in both the positive direction and the negative direction. Okay, and so that means whatever the real number output I want is, eventually the cubic function will hit it. This is not true of polynomials where the degree is even, because for example, suppose for example, parabolas will have a local minimum or local maximum. So for example, if I wanted the output of, I don't know, -3, for example, this quadratic polynomial will never hit it, right? Same could be said about a polynomial of degree 4, right? If I just, whatever degree that is, we'll make it a little more specific. That's a polynomial of degree 4. It will always have some global minimum or maximum, whereas polynomials of odd degree don't have a global maximum or a global minimum, meaning they'll extend infinitely in any direction and will hit any point you want. Okay, so I know it's a surjection for sure. Why is it not an injection? Well, it's because I can show that it has a local maximum, meaning that it changes directions. Okay, and so when I look at this function f, I don't really know what it looks like. Right? I could go through, find the local maximums and minimums, and plot it. But just by there being a local maximum or minimum is enough for me to know that it's not an injection. Because if there's a local maximum or minimum, it means the function is going to change directions. And if it changes directions, it means it has to repeat outputs that were already seen, making it not an injection, right? Because for a function to be an injection, each output can only be seen once. So all we need to show is that there exists some point where the derivative is not strictly greater than 0. Okay? So for example, why don't we take the derivative of this function? 3x squared plus 6x minus 7. Okay? And for example, I can find a value to pass into this where the derivative is positive, and I can find a value to pass into this where the derivative is negative. Okay, and for the function to be strictly increasing, the derivative will always be positive, and for the function to be strictly decreasing, the derivative will be always negative. But if the derivative has some parts where it's negative and some parts where it's positive, it means at some point in between those two, the function would have had to reach a local maximum or minimum and change directions. Okay, and so for example, f of 1 gives me 3 times 1 squared plus 6 times 1 minus 7, which is 2, which means at when x is equal to 1, the function is increasing. But for example, if I look at f of negative 1, I have 3 times 1 squared minus 6 minus 7, which I believe gives me minus 10, which means at the value x is equal to negative 1, the function is decreasing. Okay, so this means somewhere between the value x is equal to negative 1 and x is equal to 1, the function has to change directions, right? Because at x is equal to negative 1, it's decreasing, x is equal to 1, it's increasing. So at some point, I had to stop decreasing and start increasing, meaning there's a local minimum somewhere, meaning that some values will have been repeated, right? We'll have, at some point, something that looks like this, okay? And this is clearly not an injection because it won't pass the horizontal line test, okay? So f is a surjection and not an injection, okay? F prime of x is not strictly increasing. Cool. Let's look at D, the function that maps real numbers that are non-negative to natural numbers. That's given by the ceiling function. Okay, and what does the ceiling function do? It essentially rounds up to the next closest integer. Okay, or in this case, since our outputs are naturals, the next closest natural number. Okay, so for example, f of 1, so the ceiling function of 1 will just be 1. Okay, but f of 1.01, so the ceiling of 1.01 will be equal to 2. So another way of thinking of the ceiling function is the smallest integer that's greater than or equal to. Okay? Smallest integer greater than or equal to. Okay, so for example, the smallest integer greater than or equal to 1 is just 1 because 1 is equal to 1. But the smallest integer greater than or equal to 1.01 is 2. Okay, so it essentially rounds up to the next closest integer. And the question is this an injection, surjection, or bijection? And it's definitely not a bijection, okay, because it's not an injection. Why is it not an injection? Well, because f of 1.01 is equal to f of 1.02, right? And both of these map to 2, but the ceiling of 1.01, the ceilings are equal, but 1.01 itself is not equal to 1.02. It turns out there's infinitely many points that map to the output value of 2. So this is far, far from an injection. It's a surjection, though, because our codomain is a set of all natural numbers. And suppose I want the natural number 10,000 to be my output. Well, then the input I pass in will just be 10,000. Okay, so if n is some output that I want from my function, I can just pass in the same number n, and it'll get that output that I want, because the ceiling of n, if n is an integer, is just n. Okay, so f of 1 will give me 1, f of 2 will give me 2. So any natural number I want, I can make it be the output of this function. So it's not an injection, but it is a surjection. Okay, and it's important in each of these questions to remember what the domain and codomain are. Okay, because if we change that, then this might not necessarily be the case, right? For example, if our codomain was the set of real numbers, okay, that would not be the case, okay, because the ceiling function really only outputs integer values, okay? So, for example, the output of pi, which is a real number, would not have existed, okay? So the answer changes depending on what the domain and codomain are, okay? E, now we're looking at the function that takes ordered pairs of real numbers, so R2, which is, again, just the Cartesian product of R and R. 2 real numbers that are greater than or equal to 0, and the function is given by f of xy is x squared plus y squared. And I believe we looked at this example in lecture, but we can take a look at it again. It turns out this is a surjection, but not an injection. Okay? Why is it not an injection? Well, because I can easily find two different inputs that map to the same output. So for example, f of 0, 1 gives me the output 1 because it's just 0 squared plus 1 squared. And f of 1, 0 also gives me the output 1 because it's 1 squared plus 0 squared. But last time I checked, 0, 1 and 1, 0 don't look like the same point. So it's not an injection. Okay? It is a surjection, though, because pick any output non-negative real number I want. Okay? So suppose I want the output to be r, which is an element that the reals greater than or equal to 0, then my input can just be square root of r comma 0. Okay? And what would the function map this to? It would map this to square root of r squared plus 0 squared, which just gives me r. Okay? If I want the output of the function to be 10,000, I just pass in the point square root of 10,000 comma 0, and I'll get 10,000 as my output. And I can change 10,000 to be any other non-negative real number. So this function is a surjection, but not an injection. Okay, and lastly, we have a very specific example, but it's sort of there to teach a lesson, where our domain is the set of naturals and the codomain is the set, essentially, of the primes, where f of x maps to the xth prime number. Okay? So really, the mapping we have looks like this. Okay? And this is indeed a bijection, okay? And it's almost a silly example, but it's really crafted to illustrate a point. Is it an injection? Yes, because f of a will map to the 8th prime number, and f of b will map to the bth prime number. But if a and b are different, these will map to different prime numbers, right? So for example, f of 4 will be the 4th prime number, f of 5 will be the 5th prime number. 4 and 5, like the 4th prime number and 5th prime number are not the same, right? So this function is definitely an injection, okay? Notice there's only one arrow pointed to each prime number in our list of codomains, right? Is this a surjection? Yes, because our codomain is the set of prime numbers. and every prime number will appear somewhere on this list. You give me any specific prime number you want, and it will be mapped to by some element of the natural numbers under our function f. Okay, so this function is indeed a bijection. Okay, and so that wraps up our walkthrough of homework 1, and feel free to post on Piazza or email if you have any questions.